Hey everyone. Hey Sam, how's it going?
I'm doing good. How are you today? I was a little worried I'd miss first couple of minutes. My car died at like 3:15 and I had to call AAA, but I made it in time, so pretty good day.
Oh wow, okay, awesome. Did anything happen? Like were you in danger?
Nah, it started, I was like leaving my house and then as I work at a place that's not my house so that I am a bit more productive and my parents are at home and like walking around and stuff in the middle of our class. But my car died literally as I was like leaving my driveway. So it was right at the end of my driveway, it just stuck there, which
Oh wow,
was
okay.
annoying. But you're right in that it could have been much worse, in the middle of the road or something.
Oh wow, okay, yeah. I'm glad it didn't happen on like highway or something. That would be bad. Yeah. Awesome. Cool. So yeah, we're gonna give maybe a few more minutes. Just everyone, if you're here, please feel free to turn on your camera so we know that you're here. And today we're gonna get things started with the actual course material. We're gonna start with linear regression model. All right. All right. Let me see if everyone's here. All right. What do we have? We have 11 people on the Zoom. Besides Sam and I, we have 9 people. So maybe a little bit less than what I was expecting. Sam, what's the total number of students? What's that?
Missing 3. So we still need, we have 12 in the class.
12 in the class, okay. Cool, so maybe we'll give them like just one more minute to see if they join. Everyone else that's here, welcome. So yesterday was, technically speaking, the day 1, but we did a bunch of intro, walk through the course material, walk through the resources, so on and so forth, recordings, YouTube, all that stuff. So hopefully everyone has essentially everyone's on Slack, should be able to see the message that I sent, including recap and a little bit of preview. Some students from yesterday asked me, what do you like? Even homework? Is there anything we should do? Well, there isn't really a strict, deadline, strict homework, exam, nothing like that. In terms of this course, specifically in data science, just in general, my thesis is homework doesn't really do anything. This is an honest opinion, okay? This is a dead serious honest opinion. It's not a pet talk. It's not to make everybody happy, right? Homework, you essentially put a stamp on things, and you can't stamp this. Data science can't stamp it. Almost, all my coworkers, they come from non-data science background, and people are in this field because they're interested in the field. So there's nothing, nothing the instructors can do to, have you guys do a few homework and then magically, I turn you into data science. I wish that's the case. If that's the case, I give you 5 homework, you become a data scientist. That's easy, but of course that's not the case, and that's not how things work. So we're not going to do any homework, no exams, nothing like that. It's the kind of like A, it's against my philosophy of learning. B, that's just not how you become data scientist. So if any, you'll probably do more bad things to you than good things. You're gonna the homework and exams is gonna drill those answers in your head so hard that you're gonna completely distinguish yourself from the real world. And I don't want to do that to you guys. I want you guys to come up with a critical mindset and be like, hey, I'm learning this in class, but that's in class. In the real world, anything can happen, right? I want you guys to have that mindset. All right, so that's about homework. I think somebody else asked me a question. Oh yeah, so there's no more announcements on coursework. Since everyone's on Slack, I'm gonna use Slack as a main channel for announcements. So any links, any YouTube, GitHub links, code, Google Drive, anything like that will be shared on Slack. What other questions do people ask? I think that's probably about it. All right, I don't see any other questions. Okay, so I think that's probably about it. All right, let's get things started. I think we have like 10 people here, so it's pretty good. Let me get this thing started. So today's material is like this. We're gonna start with a little bit of lecture. We're gonna change style a little bit. last session, I used mostly slides in the beginning. It can be interesting, but it can also get tedious. So some students reflected the idea of doing a little more whiteboarding session. So I'm gonna draw on my iPad. But if you feel like you're a slide person, then the slide that I will be using, or I draw the materials from, is on the GitHub. So that PDF with 300 pages, that's where I draw the materials from. So if you want to follow up, today we're talking about this is technically speaking chapter. What are we talking about? So today we're talking about chapter 2, the basics in statistical learning. So let me just share my screen a little bit. Wait, hold on a second. Oh yeah, screen 2. Yeah, so this is a slide I'm talking about. So if you click in, you can go to the content. It will be introduction. We already talked about that yesterday. So today we're going to start with chapter 2. We're going to talk about statistical learning, and then we're going to hopefully jump into linear regression. Statistical learning will get you guys set up of kind of like different field, different hierarchy. What realm are we talking about, right? And then under those realm, something is called linear regression. So linear regression is kind of like the topic to guide you guys into the machine learning field. But on top of that, you need to know where you are. Okay, so with that being said, if you want to follow up, we're talking about chapter 2 right now. And then eventually we're going to move on to chapter 3. And then after that, we're going to do a little bit coding session. And then we will, my goal is to try to finish as much as I can. But let's see, time is pretty tied up, so I'll try my best. All right, so with that being said, let me share my iPad. All right, it should be coming up in just a sec. Alrighty, okay, so can everyone see my screen? Good, awesome, thank you. Okay, so what's happening? Well, we are in the field of data science, right? In data science, we need to essentially tell a story with data. So the first thing that we really need to understand is the notation of what do we mean by, when we say, hey, we have a data, right? So let's say the most simple way is, let's say I give you Excel spreadsheet. So you can kind of think of it as Excel spreadsheet, something like that. It could be just Excel format, or maybe it's a CSV. Anybody know the difference between Excel and CSV? Raise your hand if you know the difference. So the difference is this. Excel, you can edit it, and then it will save it. There's functions in there. You can link to different sheets. You can use the VLOOKUP. You can use all that stuff. CSV, it's static. You can't save any functions. You can't do any links, call outs. You can't call functions. You can't write anything in there. So the difference is Excel, it's functionable. CSV, it's just purely number. There's no formulas behind it. Okay, so if you have a formula, let's say A plus B, right? Cell C equals to cell A plus cell B, something like that, very simple. If you save as a CSV, you will lose that A plus B. It will just be whatever the result is, and that's it. You will lose that formula. Versus if you save in Excel, the formula preserved. It preserves in the cell. Okay, so that's the difference. Typically, when we load a file up to Python, we're pretty much talking about this format. Because if you load out a function, it will still run, no problem at all. But sometimes when you export it, you might do some weird things. So typically when people say, oh yeah, load up an Excel spreadsheet on Python, whatever. Like when people say that, they're usually referring to CSV. Just like a static data, CSV. So what this is going to give us is essentially a data frame, right? Data frame has rows and columns. So I'll say rows can basically be like this. Let me make it straighter. And then columns, maybe it's like this. And then we're gonna give them some name, right? Because how do you refer to this number, right? You're gonna have to have some sort of coordinates to refer to this number, right? So the idea is this: typically, when we're given an Excel spreadsheet, we refer the rows to this index I. This is I equals 1. This is I equals to 2. I equals to 3, and then so on and so forth. Okay, and then we also have columns. So let me erase a couple of these things because they're gonna confuse us. Let's say that's your table. As simple as that, right? As simple as that. That's your table. Now, obviously, you can continue here. You can continue here. But let's say that's our table. This is gonna be column 1, column 2, column 3. And column, we typically use the notation J. So I and J. So of course, this is J equals to 1, J equals to 2, J equals to 3. Okay? So now you say, okay, I'm interested in this number, whatever that is, right? So instead of saying, a bunch of sentences, then you say, hey, why don't we look at, let's call this data frame X. So data frame, let's call it X. Then what this means is this essentially is denoted as Xij. I equals to, well, I need to move this a little bit, right? Because I erased something. All right, so now it's clear, right? So now it's this guy and this guy, right? So now you have a coordinates. Everything is clear, right? No questions asked. So I equals to 2 and j equals to 2. So in other words, this x22 is exactly this red mark here. Okay, so that's what we're talking about. Whenever people say a data frame, this is what we're talking about. And X is the entire matrix, and then there's I and there's J. Okay, so this is kind of like you can kind of think as a vector form, right? So what a vector form means is, this is kind of like a vector form. Now there's of course also matrix form, right? Matrix form, as you can probably imagine, is going to be a matrix. So what that means is we can also write x11, x12, x13, x21, x22, x23, and so on and so forth. This is x31, right? So on and so forth. This is, of course, going to be a matrix form. And the good thing about matrix form is matrix is constructed using vectors. Okay, so what do I mean by that? Well, each column you can kind of think as a vector, and each row you can kind of think of as a vector. So I can slice it, I can take a range, I can do whatever I want, right? We saw from yesterday's lecture that you can load up a template, right? Load up a CSV, California housing, right? And then you can do brackets, right? 0 to 3, 0 to 4, it will give you like the first few rows. And then you can do another 0 to 3, 0 to 4 that give you first few columns. And then you can subset it, you can slice it, you can take a column out, you can do whatever you want, right? So how is it possible? So how do we make all those operations possible? It's because matrix is made in terms of vector. And each vector, you can kind of call it, and then it's by itself an object, such that later on you can retrace it back to wherever that is. So typically you can say something like this. You can say, if I say x, j equals to 2, right? Then I know that you're talking about the second column. So whenever you write something like this, I know that you're talking about this column here. So this is what you're referring to, right? Very clear, no questions asked. Xj equals 2, that's it, that's a column, done. Okay. So now, with that being said, I'm going to introduce you this first notation. It's called a sigma. So for those of you who took calculus, this may be a little bit of a review for you guys, right? The first signal is called a sigma. So this is Greek letter sigma. So sigma means sum. Okay, so it means sum. Now, one thing about this letter is that it cannot exist by itself. If you just write sigma, I actually have no idea what you mean. right? You need to give me some sort of rounding index, and that's how this letter is defined. If you write something without a rounding index, unless you say it, then maybe you don't have to write it down. But if you just write it down, you don't say anything, and you have a bunch of letters behind it, then who knows? No one knows what you mean. Okay. So really, whenever you say something like, let's say sigma I, right? And then maybe you say I equals to 1, 2, 3. Then this means what? 1 plus 2 plus 3. Does that make sense? So that's kind of, so maybe you've heard of a geometric series, maybe you've heard of harmonic series. So those all are written and represented by essentially this Greek letter sigma. Okay. So here's a question for you. How do we what's a mathematical way of adding all those numbers together, right? Let's say the goal is to or let's say question is how to sum all entries together in X, and X being distinct, right? How do we do that? Well, there's an easy way, there's a dumb way. There's a dumb way and there's a smart way, right? The dumb way is you say, okay, I'm gonna write every single number out. Okay, I'm gonna do that. So how you do it is you say x11 plus x12 plus x13, da 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 da. And then you're like, okay, x21 plus x22 plus da 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 da, and so on and so forth until you hit the last one. Okay, let's give it a range. Let's say this is all the way to, I'm gonna move this here. All right, let's say this is n by p. So assume it's n by p. So what that means is you're gonna have all the way here to xn1, and then you're gonna have all the way here to x1p, and then da 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 da. Here you have xnp. So n is number of rows, p is number of columns. So n rows, p columns. All right. So let's say that's a situation, right? Then what that means is you're gonna have what? You're gonna literally write this out, right? All the way to what? 1p plus da 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 da, 2p plus da da da, all the way to plus np, right? It's gonna take forever, right? So you kind of get the idea. This is the stupid way. So dumb. Right? There's also of course a smart way, right? A smart way is very elegant. So sigma I, sigma j, xij. Done. Okay. One letter, one line. Okay. 2 sigmas, 1 letter ij. Done. Okay. So that's why, when we introduce calculus, sigma is like the first thing that we introduce. And then of course you can make it continuous, and then it'll be integral. Also, integral is just basically sigma but continuous. Okay. So that's kind of what the situation is. Of course, you can say, hey, I'm going to use vector form, right? So you can say, well, I'm gonna just do this, right? Yeah, you can do that. But when you do that, notice that each of the xj is going to be a vector, right? So this needs to be something like this: x1, x2, xn, j equals to 1, plus x1, x2, xn, j equals to 2. And then da 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 all the way to x1, x2, xn, j equals to p. So you can also write like that, right? All these are valid, okay? But there's a small caveat here that's a little bit unclear, okay? So if you write like this, that's fine, but then you need to tell people that in the end, you don't just get a big matrix. You don't get a one matrix, right? It's very easy to come up with something like this. So you're gonna have to sum these numbers up, right? So then you're gonna tell people, you say, okay, once you're here, you have to do this. I from 1 to n, xi. So you have to sum these guys up to be able to get the entire sum of the matrix. Okay, so that's just a small caveat here. In other words, the vector form is kind of like, this is reducing your work? Maybe you're writing a few lines of code, but essentially you're gonna have to do this one and also do this one, right? You're gonna have to do both. Okay, so that's kind of what's going on here. You know, if you know programming and you know programming well, you're gonna prefer to code this way. It's maybe easier than code this way, right? If you do this from scratch, it's a kind of like a double for loop. But if you do this way, you just need to add a bunch of vectors together. And it's just from programming perspective, this way is maybe a little bit more efficient. Okay, but both ways should lead you to the exact same results. If they give you different results, then please check your code, something's wrong. Okay, all right. So that's just some basic notation I want to tell you guys. Now, with that being said, you have an understanding, right? You kind of know what the data is talking about, and we have a way to track which location you are in the data set. And not only that, we can track columns, we can track rows. They are all just by itself vectors. Okay. So that's kind of like the setup. Now, with that being said, the next step is to essentially take advantage of that, right? Let's say you have a data frame. Let's say you have let's say you have x11, x12, x1n. This is x21, and then so on and so forth, all the way to xn1, xnp. And then let's say this is your data matrix. And then the first thing to talk about is, what are we doing here? What are we trying to predict? In data science, it's all about what you're trying to predict. Okay, but we say prediction kind of take for granted. It's not really about prediction. It's about finding the function or finding the map. That's the more important part, and that's mathematically sound. Prediction is not really mathematical sound. Okay, but prediction is kind of like a cool word that people use. Predict, like you kind of know the future, right? That's why people say prediction a lot, kind of for granted. But the real situation here is, like, the real language here is, how do we break things down such that we can find a relationship? Okay, it's your job to define what relationship it's in between, and that's your job. So you need to tell us what is x, what is y that you need to predict. A good data scientist usually has a sharp eye to tell what are those things. Okay, so I'll give you an example. Let's say you have a data frame. This is where you collect the data. That's a column, that's a column, that's a column. Maybe this is a number of bedrooms. So I'll quickly write like this. This is maybe number of bedroom. And then maybe this is number of living room. And then maybe this is sales. House sales price. Okay, so it's your job to say, okay, let's learn from these guys and let's predict this. That's your job. Okay, it's not other people's job, it's your job. Okay, so really make sure that you have a hand on this. If somebody else give you data and be like, oh yeah, let's predict this guy, let's learn from all of these, let's predict this guy, you should question him why. What's the value here, right? You should question him. So the first thing in data science is, you need to know and you need to tell yourself as well as the computer what is x and what is y. Okay, so that is going to be the realm of what we call supervised learning. So here, let me write it here. So first concept is called supervised learning. And then of course there's also unsupervised learning, right? So we also have wow, that's terrible. Let's rewrite that. Unsupervised learning. So you have this guy and you have this guy, right? What's the difference? The difference is, in supervised learning, your x and y are given. Okay, so in other words, y is your target. This is your target. And then x is your features. Okay, in unsupervised learning, you're only given x. There's no y. Okay, you don't know what y is. Okay, so usually in complete real world where there's no instructor, no teacher, no one's helping you, right? Absolutely no one's helping you. You don't have a paper, you don't have anybody. This is a complete new data set, right? Let's say that's the case. Then usually you're gonna have to start from here, and then you're gonna have to somehow build up that domain knowledge, and then you should be able to have the sharp eye to say, oh, okay, this is interesting. Let's predict this guy. Everyone else I can learn that from. Okay, so really in real world, if there's no paper, no instructor, no school, nothing like that, nothing exists, right? If there's nothing exists, then you're in this field. Okay, so some people ask, okay, why is this interesting? Unsupervised learning is a step up to what we consider artificial general intelligence. This is going to be an important concept. This is called artificial general intelligence. So what that means is maybe short for AGI. Maybe some of you guys heard of this, AGI. So why do I say this? The reason I say this is because the next 20 years of development, either from data science perspective or from machine learning perspective or computer science or computer engineer, people are mostly trying to automate, like the first stuff here, like this stuff, you can almost guarantee to automate it. And you come to school and you learn this stuff. And then when you go out of school, I show you the package, I show you where to get the code. You can productionize it. And it's there, right? It's automated. So what you cannot automate is this thing, right? And it's precisely the reason I just said. You define, right? Humans define what is this y is. Okay. If you don't know what y is, you have to start from here. And then when you start from there, who knows, right? Anything can be y. Anything I can predict, right? Then that's a matter of choice. The computer doesn't know to make that decision. Like once you define it, everything else computer can take care of. But if you just give me this, then computer doesn't know what to do. Okay, so that's gonna be an important part of your career. But in terms of tutorial, in terms of teaching, especially in an intro class like this, typically we start with what's going on here and what can we do here. Okay, so the idea is now that we're in the realm of supervised learning. So in supervised learning, now what's the next step, right? The next step is to build a relationship between X and between Y. Right? This what's going on in between, that's what we're interested in when we're talking about supervised machine learning. So in other words, it doesn't matter who gave you the idea. Maybe you figure it out yourself. Maybe you read a paper. Maybe you go to class. Maybe your boss tells you that, right? It doesn't matter where the source come from. You're gonna have to know what the y is. Okay? And in that case, depending on what y is, you have different models. So the most simple case, y is continuous variable. Continuous variable can be whatever, right? Anything you can kind of define as continuous variable. So let's say housing price, right? That can be a continuous variable. So mathematically speaking, continuous variable, you can kind of think of a real number. That's kind of like the set in the real set, right? So if sometimes you hear people say A belong to R. This R means real set. So this means real set. And then this A is just a fixed number. And then this symbol means belong to. Okay, so a number belong to a set. So that's how people write it. In this case, it is continuous, but it's a special case because the housing price can never be negative, right? If you say, hey, this house costs negative $1,000, I have no idea what you're talking about. Like I thought you're telling a joke or something, right? You pay me $1,000 to buy a house. That doesn't make sense. It doesn't make any sense. So in this particular data, yes, we are talking about continuous, but no, there's no negative values, right? Housing price has to be like some positive number. So that's kind of like the situation that we're talking about. So in this case, let's say you look at an example, right? So housing price. So housing price, let's say $1,000, right? So if someone you say people say then in this case, this A is going to be in a real set, but you have to write a plus. Plus means, this plus basically just means A is in this number and A is positive. Does that make sense? So it should be very well defined, and once I write it out, everybody should be on the same page of what we're talking about. So now we have a setup, right? We know what our data is, right? This is our data, it means right here. And we know what we're trying to predict. This is what we're trying to predict, this column. Everything should be clear, right? So then you say, okay, now why don't we build a relationship? So the model here that you need to construct is it's actually a linear regression model. And a linear regression model is a relationship. Okay, it's a relationship tell you how to go from X to Y. So really what we're trying to say here is to find this function f such that you can do a prediction. So first thing is you can call it 1. So we can predict y by computing y hat equals to f of x. Okay, so really I'm kind of abusing notation here. So I'm going to erase a few things and I'm going to write again, but I want to write this way to showcase what I mean. When you have a relationship f, you throw x in there, it will give you a prediction. Okay, but now here's the problem. I'm actually abusing notation here. This f is kind of like a there should be innately some sort of real relationship between f and the fake and the predicted f, right? Because the relationship is also guessed. It's not I can never know in Mother Nature what is the difference between, or what is the function between number of bedroom and the house sales price, right? I can never know that, and you should convince yourself you will never know that, because that gives you the mindset of your models can always be improved. Okay, so basically, in other words, right, in plain English, don't play God. Okay, if you don't know something, just admit that. So no models are exactly same as the real relationship in real world. Okay, you might find a model that's similar, that assimilate the relationship in real world very accurately. That's possible, but that's very unlikely to happen. Okay, there's always some sort of error there that doesn't matter what you do, you just can't learn that. Okay, so you're gonna have to accept that. So it's good to set up in the beginning. So sometimes you say people write, okay, this is the real situation. This is a real function, real relationship. People write this, and then there's also estimated relationship, and then maybe people write this, but with a hat. So that hat means it's a prediction, it's an estimate. Okay, it doesn't matter what this function is, it's not a real one. Real one, no one knows. Okay, so let's put a note here. No one knows. And then this one is found by you. Okay, so you should accept that they are not exactly the same. So with that being said, now I can continue to tell you what is the next step here. The next step, right? We haven't finished this. So the linear regression model is an F such that you can make this prediction, but also under some sort of constraint, right? Because if there's no constraint, I can do whatever I want, right? Then that's not going to work. So there's some sort of constraint. So the constraint is, so you say under constraint, this prediction. So y is a truth, and the prediction y hat. So this is a prediction. So this and this are very close. Okay. So in plain English, what I meant by that is, what is very close? Well, very close means the two numbers are very similar, right? If your y is 1 and I give you a 1.1, you can kind of say, hey, that's similar, right? if your y is 1 and my prediction is 10, that's not similar. That's far off. So that model is going to be bad, right? Versus if I'm prediction is 1.1, that's a good model, right? So this is a good model. This is a bad model. Okay, good and bad. There's no strict saying good and bad. You almost always have to have a comparison. You have to have at least two models. You say, hey, this is a model 1, and then this is a model 2. Model 1, the error is 1. Model 2, the error is 9. That's the difference. Now I know which one's better, which one's worse. Okay, if you just give me one of this guy, I have no idea what you're talking about. Okay, so this is kind of like I just want to. So this is just to set the tone of like what do we mean by when you say a model is like good or bad, right? In regression, please don't use the word accurate. Okay, accurate is not defined under regression problem. It means nothing. Okay, people tend to like I hear this like when I was working as a trader on Wall Street, people say this all the time, right? Hey, my model says tomorrow stock price is going to be 100. It is actually 100. My model is accurate. That sentence means nothing. Okay, it means nothing. It doesn't mean anything. Terminologies are completely wrong. Nothing can be done here, right? There's no conversation continuing on. Okay, or people could be like, well, my model gives make a prediction of $100 and turn out the stock price is $120. It's not that accurate. That sentence means nothing. Okay, once again, it means nothing. I don't know what he's talking about. The terminologies are completely wrong, and I don't know what accuracy means. Okay, so when you are in a regression problem, try to use a language that's, hey, my model is on average 1% deviate from ground truth. Use that language. That is what regression means. Okay, I'll show you guys an example. So now I can show you guys what is a regression model. So now you kind of know that y and y hat needs to be close, right? So what do we mean by when they're close? Well, there's a loss function called MSE. I'm going to write it down for now, put a note, but then we're going to go through this. So when I say close means loss is small. And then you're like, okay, what is loss? Well, the famous loss function is defined as mean square error. So famous loss is mean square error. Or sometimes you hear people say MSE, right? But we're gonna walk through this. So first things first is you do your linear regression first, right? You do your linear regression first. So what's happening there is a regression model looks like this. Y equals to beta 1, let me start with beta 0. Beta 0 plus beta 1 x1. This is just, you can kind of call it univariate. It just means that there's one feature. That's it. Okay. Or you can do beta 0 plus beta 1 x1 plus beta 2 x2 plus all the way to beta p xp. This is, of course, a multivariate. All right? So you have univariate, you have multivariate. Multivariate just means that you have a couple of features you want to learn, right? If it's univariate, maybe you just have one feature. Let's say number of bedroom. And then this is house price. So housing price. And then for multivariate, obviously housing price stays the same, right? But then maybe you have number of bedroom. But then maybe you have something else, right? Maybe you have number of living rooms. And then who knows, number of bathrooms, square footage, whatever features that's in the data set, right? So now you kind of get the idea. Oh, a linear regression model means what? Linear regression model means it's linearly additive, okay? What's linearly additive? Something plus something, that's linearly additive, okay? In very simple scenario, let's say I'm taking this model as an example. Really, you can kind of think of it as the following graph, which I may draw here. That's one axis, that's another axis. Maybe this is X, maybe this is number of bedroom. And I'm using number of bedroom to predict the housing price. So this is housing price. So that's going to be my, that's X, that's going to be my Y, right? And then a linear model is essentially a line, a straight line. So if your data set is fall under, let me just draw a line first. Let's say that's your model. So Y equals, so maybe that's your model that says Y equals whatever this is. Let's say this is 1. So 1 plus, let's say the slope is about 1. How about that? Make it easy, right? Very simple, right? 1 plus x. 1 plus x is what? It's a line, right? So now notice that what could happen in here? The data maybe is going to look like this, right? The data is going to maybe look like this. It's a bunch of scatter plot, right? Let's say this dot. This dot maybe has some sort of number of bedroom, and then has some sort of housing sales price. Same with this dot, right? Number of bedrooms, price. And then with this dot, right? And so on and so forth. Every dot, you can say, hey, I have a coordinate. This is the number of bedroom. This is the housing price. Okay. So now, exactly what is linear regression doing is it's looking at the each dot and how far that dot is to its prediction. Okay. So think about this way. In a very simple scenario, let's use a green dot, right? This is a sample case, right? Let's say this green dot is here. Very simple. Let's say the green dot here. What is number of bedroom? Well, you look at the x coordinate, right? So that's here, x coordinate. And whatever number of bedroom, let's say 3, right? 3. Then what you're going to do is you say, okay, we have a prediction, right? So what is the housing price? Housing price is 1 plus 3, that's 4. Then 4, maybe it's here. Maybe that's 4. Whatever that means, right? $4 million, $400,000, whatever that means, right? So that's, sorry, I messed up here. It's not 4. So if you look at the prediction, the prediction is actually here. This number is 4. And this number, if you look at the data, it seems there's a difference here. It's less than 4, right? So maybe this is 3.7. So 4, it's a prediction. 3.7 is a ground truth. Okay, so let's write that down. Just in case I don't mess up again. So this is the prediction. Yeah, this is a prediction. And this is a truth. Okay, so in other words, 4, that's here, 3.7, that's here. Okay, so there's of course a difference. The difference is exactly this purple small line segment here that I'm drawing. This is the distance. Okay, so this distance is also called the error. It's precisely the error for this number 3, right? The prediction from number 3. Okay, so you give me this number. I send this number into the model give me a prediction that's there, and then I compare this prediction with the actual ground truth. There's a difference. That difference is called error, right? It's a mistake, right? It's a mistake, right? So how much mistake this model is making in this particular case? Well, it's 4 minus 3.7. That's a difference. Okay, so linear regression is to minimize this difference for all of the data points. Okay, in other words, every data point has a difference, right? So what do I mean by that is I can essentially draw out this small purple line for all of data points, right? Let's say this guy's here, this guy's here, who knows, this guy's here, maybe there's a dot here, there's a dot here, there's a dot here, there's a dot here. Does that kind of make sense? So these purple lines all together is going to be what I want to minimize. And that's precisely what linear regression is doing. Okay. So you might get confused, right? Well, how do we do that? Well, I have a couple of options. I don't have all of the options because linear regression is kind of like a pretty simple model. So I have some options. I don't have a lot of options. So what are my options? Well, if you look at the model, it will tell you beta 0 plus beta 1 x1. x1, if it's 3, then it's 3. There's nothing I can do. That's just what the data tells me. I can't change the number of bedrooms in a house just simply because I want to have a more accurate model, right? So that's not going to be an option. So my option is to change this guy and change this guy. So these two are my options. I'm allowed to pick whatever number that I like, right? So here's an idea. Let's say you have a situation, right? Let's say you have a situation. How do I do this? I'm going to I'll recreate this graph somewhere else. Let's see. Actually, I have a here. Let's do this. I want to preserve this graph, so I'm gonna copy, and then I'm gonna put down here. Boom. All right. All right. Awesome. So let's say situation 1. I'm gonna call this scenario 1. So scenario 1, let's say my dots are, let's say I have a couple of dots here, right? Like this. That's my data, right? Couple of houses. The house here has coordinates this and this. House here has coordinates this and this, right? I have a couple of dots up there. So what I'm gonna do is I'm gonna rotate my regression model, right? So before, what do we have? We have 1 plus x, right? So that's what the y line says. So this white line, 1 plus x. Well, that's not gonna work because a couple of these errors are pretty high and they're all up here, right? So that's the bad model. So what I'm gonna do is I'm gonna rotate, and then now my model is gonna go from this white line to this orange line like this. If I'm doing that, then I essentially have a slightly different model, right? Because if you look carefully, this might go to here, right? So this might be a negative number, right? So if I may, I can extend this, and it's going to be here. Who knows? Maybe it's minus 0.8. And then the slope of obviously it's going to be sharper, right? It's slope. It's a deeper, right? It's a much higher incline. So what that means is if you can to demonstrate this part, you can draw a line. Let's say you draw a line like this here, and then you can draw a vertical line to here and a vertical line to here. Since this distance is higher than this distance, that means what? That means the slope is sharper, right? So if the slope is sharper, then this model is no longer 1 plus x. It's going to be whatever this number is. Let me use a different color because I use orange to draw the line. So now this is going to be minus 0.8 plus a sharper slope. So who knows, maybe 2x. Does that make sense? So you're rotating and then you shift down, right? So when you do rotate, you change this number and this number. Another word for this these numbers in the middle. So this number and this number, this is called an intercept. And then there's this number, and there's a hidden 1 in front of it, right? Because 1 times anything is 1. There's this number here. This is called a slope. Slope. Does that make sense? So that's kind of the situation here, right? So in other words, I look at the linear regression model. So here's my model. I am trying to minimize the loss of y and y hat by controlling beta 0 and beta 1. Okay, so this is going to be the first very how do I say this? The first very statement that you're going to see. This whole thing is called an objective function. Okay. In machine learning is built upon operation research, which essentially is optimization. Every machine learning problem is an optimization problem, and eventually you're gonna all get into the habit of speaking in this language. Okay, you do something and then the loss is smaller. Okay, or you do something, the reward is higher, and that's kind of the machine learning world that we're still in right now, which is essentially to understand this statement. Okay, so first of all, this is an objective function. Every machine learning model must have an objective function. You have to tell me what this is. Otherwise, I have no idea how to build this model for you. Okay, so that's the first thing. You have to tell me what this is. And then second, you have to tell me, hey, you have a loss, right? And we're going to talk about loss in the next hour, but you're going to have to tell me what loss that we're talking about. So there's going to be some sort of loss function here that tells me how far apart this y and this y hat is. Okay, if I'm taking a look at the distance, well, then that's a minus b, right? That's the distance. So you're going to tell me what these things are, what loss is, and you're going to tell me what is it that am I allowed to change. Okay, so let me write this down. This is going to be important. So this is the truth, and this is the guess, and this is the loss. And these things are parameters. Basically, parameters means my choice to change the model. Make sense? So this couple of letters here, this is all I need. If you can tell me what each of these things are, that's all I need to be able to build a model for you. And we're going to take a look using linear regression as an example in the next hour. How do we implement each part of this? Okay. All right, it's about an hour. Let's take a break. And then let's take a little bit longer break. So 6:05. I'll come back at 6:05. Right now it's 5:53. So about 10 minutes. All right, take a break, and I'll see you guys in 10 minutes. Hello, hi, welcome back. All right, let's give a few more seconds for people to join and turn on their camera. Cool. Okay. So yeah, do a quick recap. I think someone was asking me this question. So let me share my screen. So first of all, Slack channel. Everyone hopefully should be having this already. I see a bunch of people join. If you still have questions about this, let us know, and we'll figure out a way to help you out. But this is gonna be where I send the recap and the summary and whatever to-do list, announcements. It's gonna be here, and every day I'm gonna start posting things on the end of the session when the class ends. So please make sure that you have this open and you're definitely joining the Slack channel. Yeah, so that's first thing. And then you see a couple of links here. Most of these links are essentially the same link throughout the entire class. Okay, I'm not gonna give you like one GitHub for day one and another GitHub for day two, right? Chances are it's all gonna be put together. So day one, day two, they're all in the same folder. Okay, so you don't need to save everything every day. Like you just save it once, and then every day you come back to the same location and you check. Okay, so I think someone asked me a question there. Yeah, Zoom link, Zoom recordings, they're on coursework. You click on it. Let me know if that's a problem. And then I think everything else should be straightforward. Most of the materials, I have a YouTube channel to cover the materials in case you missed. We also have the Zoom recording to cover the same material. So in case you missed, there are two locations that you can check. One is the Zoom, and the other one is YouTube. So this way, you don't have to be afraid of missing any material. Okay. And then in addition, there's this code is saved here on the Google Drive link. Okay, so somebody was asking me this. So Google Drive link, if you click on this, it will bring you to this folder. There's tutorial button here. And if you click on it, it will bring you to basically two folders. The first one is exercise deep learning. These are all neural network based models. So we're not there yet, but we're gonna be using that essentially the other half, like the rest half of the program. Right now we're in this folder, ML, machine learning. Okay, so anything that I'm coding, anything related to code or nodes, concepts, they can all be referenced from either of these two folders. And if you come back, there's also this class notebook folder. So class notebook folder is just whatever I typed in class. So it should be a subset of that previous two folder that I showed you guys. But maybe, because we're talking about things in class live, right? And sometimes people ask questions. So I have these notebooks set here as well, just to help you recover the order of topics happened in class. Because we may or may not follow the slides, right? All right, so that's pretty much where things are. And then somebody was asking me the lecture slides. So lecture slides is saved on here. Introduction, oops, sorry. Introduction, there we go. Okay, so let's start fresh. That's the main GitHub page for this course. And I'll send you guys just double confirm. All right, and then you go to script is the same thing, but it's somebody asking slides, right? Slides is here. So you go to docs, that means documents, and then go to big data machine learning. You click on that, and it'll bring you here, 2022 summer. You click on that, and then the slide is here, PDF, right? You click on it, that's where it is. You can of course download it, right? Download button is here. So top right, that's the download button. So this PDF is quite large, right? You scroll down, it's like almost 300 pages, right? I think like 290 pages or something. It's a large document. Other than that, I think it's a pretty straightforward. Somebody else asked me a question about the PowerPoint that I did. So the PowerPoint is back in Google Drive. Okay, so the main folder, orientation, and then if you click on this, with just one moment, it will be here. So if you want, you can go through this when you're doing the project. Okay, so this is the main site I use to introduce a project, and everything's here. All right, okay, so that's the folder. That's pretty much a logistic question somebody was asking. Cool, awesome. Any questions? Good. All right, cool. All right, so let's stop share screen and then let's go back to my iPad. All right, it should come up in just a sec. All right, can you see my screen? Good. Thank you. Okay, thank you, thank you. All right, so let's get started. Okay, so as a recap, what happened, right? So first of all, we introduced a data matrix, right? Xij. That's how you denote vectors, rows, so on and so forth. And then each vector can be a variable, can be a feature. You either learn from it or you predict it, right? So that gives you x and y. And once you know x, once you know y, you build a model. The easiest model is just draw a line, right? That's the easiest model. So what's a line? Well, this is something like this is a line, right? You draw a line. And what controls a line? The slope controls a line, right? Because you need to know how deep it goes, right? And then the intercept also controls the line, right? Because it changes your position, right? It's +1, you go up a little bit, right? +2, you go up a little bit more, right? Or -1, go down, right? So those are things that you're allowed to do to change the line. So based off those idea, which is a mathematical idea, right? They're mathematically sound on the graph, right? It's well defined. Right? Based on these ideas, we can then talk about machine learning, right? What is machine learning? Machine learning is essentially understand this formula here. You want to first of all minimize your objective function, which is your loss function, and loss function has to have two inputs: your ground truth, right? Truth, and then your prediction, or whatever guess that your model is having. So truth and guess, or truth and prediction. Maybe I should say prediction because that's just a slightly more professional. Prediction. You give me these two things, and then you tell me what loss function that you're using. I'm able to calculate some sort of error, right? It's a numerical number. It tells me how different your guess is from the truth. If these things are too far apart, obviously it's a bad model. If these two things are very close to each other, then it's a good model. And then in addition, you need to tell me what are my freedoms, right? You need to tell me what are the things that I'm allowed to change. Well, these things are what I'm allowed to change, right? I can change the slope. That's going to be the beta 1, or I can change the position. So that's going to be beta 0. Okay, so now with that being said, this I'm going to take it out, and I'm going to expand it, okay? So bear with me. All right, so let's write out the, so we're going to expand the objective function. So here we're going to say expand objective function. All right, so what that means is I minimize my loss function by controlling beta 0 and beta 1. So what do I mean by that is, let's say model. Model is a linear model, right? Linear model means it's linear additive. So it's beta 0 plus beta 1 x1. That's my model. So in other words, if I give you some sort of x1, the prediction is actually y hat, right? So really, I should be writing something like this. I should be putting this here. I should be saying y hat equals to fx, where f is linear model, right? So now everything is clear, right? F is linear model. I throw x in there. It gives me some sort of prediction. So notice that this y hat, right? Once again, this y hat, I actually made a mistake earlier. Y hat, it's what's on the line, okay? It's not the ground truth. It's what's on the line. This number 4 here, that's the prediction, okay? So now with that being said, you can essentially plug all of this in here, right? Because that's where y hat is coming from, right? And we have the model, right? Why don't you just use it? But that's the idea. So how do I do that? Well, I plug it in, right? So plug in is very straightforward. So you say you want to minimize your loss function y and y hat. What's y hat? Y hat is beta 0 plus beta 1 x1, right? You plug this in here, right? And you plug it in. So once you plug in, now it's a little bit more clear, right? So I'm controlling beta 0, controlling beta 1, and then something changes with the loss function. And then your goal is simple. Your goal is to minimize that, right? So here, we haven't talked about what is the loss function, right? Here's what I'm going to give you. The first most important equation is called a mean square error. So mean square error, remember that I wrote a little bit up here, right? This is a mean square error. I am going to put in a box. Right, that's my mean square error. And then I need to define what that is. So here, I actually need to define, so choose mean square error. Mean square error is defined as, so this is 1 over n summation I from 1 to n yi minus yi hat. Okay, so what's happening here? Well, you have whatever this is and divided by n, right? So this is the easier part to understand, right? You give me something and I divide it by n. That's because it's an average, right? There's an n sample size. What's the average loss? You divide it by n. So this part is easy to understand, right? So then what's happening here? Well, recall that earlier we talked about the sigma, right? We talked about how to navigate through data using calculus, right? So recall in the previous hour, where's my sigma? Here, right? We spent all that time talking about what's my row, what's my column, how to index your data. We spent all that time talking about this, right? So now we're going to put it to use. How do we put it to use? Well, if your data set has n samples, right? So n is n samples, and then each sample there's a ground truth, there's a prediction, right? So you're not gonna write out every one of them, right? What if you have 1,000 samples? You're gonna copy 1,000 like numbers? No, right? No one writes 1,000 numbers. You write out in summation form, in vector form, in matrix form, right? That makes your life easier. So this basically means 1 over n y1 minus y1 hat, obviously squared, right? Plus y2 minus y2 hat, and of course squared, plus plus all the way to n, yn minus yn hat squared. But of course, I'm kind of running out of room here. So what I'm going to do is I'm going to move this to the left. Right. And then I'm not done here, right? Because this is a multiplication. So I need to add another parenthesis, right? Otherwise, you can't factor out, right? Then that's wrong. So I obviously need to add one more bracket like that. That's going to be what the first formula means, okay? So you go to your first sample, right? You go to the first sample, you say, well, what is your y? Okay, the model guess y is to be whatever number. You take the difference, you take the square, and then whatever this is, you save it here, right? You do the same thing for second number, save it here. Do the same thing for last number, save it here. And then you add all of those square laws together and divide by n. That's going to be your mean square error. Okay, so so with that being said, you can even write a little bit more. I'm not going to do too much. I'm just going to write out like the first one of them. Instead of that, so this is actually what? This is actually just beta 0 plus beta 1 x x1, right? So if you want, you can like write the entire thing out. Like that's kind of like if you want, you can kind of think like that, right? So okay, so with that being said, now you're kind of off a good start, right? So you know your loss function, you know ground truth, you know your prediction. The rest is just math, right? You work out the math. So let's plug in. Oops. Let's plug in. Minimize. The loss function we talked about is what? 1 over n summation 1 I from 1 to n yi minus parenthesis beta 0 plus beta 1 x1 squared. And then by controlling beta 0 and beta 1. So in other words, I'm allowed to change this number and this number such that this prediction plugged into this loss function is making this entire formula smaller. Okay, so that's what machine learning is all about, right? So once again, I'll repeat that again. So I'm allowed to change this number and this number, okay? So I'm changing this number and this number. They are the parameters of the model. So of course, if you change parameters, the prediction changes, right? That's the whole point of this. So this change. But this change in what way, though, right? In what way? You need to tell us, like, in what way. This changes in a way such that when you plug this into the loss function, the entire loss function value, the numerical value of the entire loss function is smaller. Smaller, the better. Okay, smaller, the better. It means you are not making that much mistakes. Okay, so that's the most basic setup of what you're supposed to do and how you're supposed to do things. And then from here, the idea is well, how do we find beta 0 and beta 1, right? How do we find that? Well, there are a couple of ways. There's actually more than one way to find it, okay? The first way, which is kind of like the easiest way, it's kind of like the mathematical way, is you kind of set up like a two equations, two unknown, and you solve it. Okay, so that's one way. The other way is you can use gradient descent. Okay, so either way works. It just kind of depends on like your own preference. Okay, so if you want to follow up in the slides, I think someone is looking confused. So if you want to follow up in the slides, I am talking about I think right now I'm talking about linear regression, which is chapter 3. Okay, chapter 3 in the slides. Linear regression. Okay, so all right, so let's quickly through. I probably won't be able to go to the derivation. You guys will do that in undergrad school. But let me quickly go through what are some ideas here to find the best sets of beta 0 and beta 1. Okay. So there's a easier way, there's a difficult way. The easy way is to look at the formula and say, oh, wait, hold on one second. There's two unknowns, there are two equations. There must be a unique solution, right? And that's exactly the case. In linear regression model, specifically one feature, it's called a univariate linear regression model. There always has one solution, and it's a unique solution. Okay, this has to be true. Like if I run a model and Sam runs a model, our answer better be the same. If there are different answers, one of us is definitely wrong. Okay, so that's kind of the situation here. You can kind of say, like, some people tell me, well, doesn't that mean the linear regression is a little bit stubborn? It's like inflexible. It is inflexible. That's the whole point of this. Yeah, it is. So it only has one solution, and that's it, right? So how do we do that? Well, two ways. First is, let me just write it out first. So the question here is how to find the best parameters. So basically the best beta 0 and beta 1. Obviously best at the same time, right? Not just beta, not the best beta 0, the best set of beta 0 and beta 1. Okay, so sometimes maybe you hear people say something like this. That's exactly what this is, right? It's to differentiate the set of beta 0 and beta 1 versus beta 0 by itself or beta 1 by itself. right? If you just optimize beta 0 by itself, that's no point of that, right? Because you need the both parameters to be the best at the same time, right? That's the whole point of this. So the first thing is to set up the equation. So first solution is I'll say solution. Solution. First solution is two equation, two unknown. The second way is gradient descent. Okay, two ways. First one, two equation, two unknown. Second one is gradient descent. Okay, so let's talk about the first one. I won't derive it, but I'll just set it up for you guys. So this is a loss function, right? This is a loss function. But if you look carefully about this formula just for a little bit, it turned out that you have a what do you not know, right? Like everything else you know, right? Yi you know, xi you know the sample size. Then there's pretty much everything you know, right? The only thing unknown is this beta, right? Beta 0 and beta 1. But that's the whole point, right? We're trying to find them, right? Of course, you don't know it in the beginning, but you're trying to find them. So the two unknowns refer to beta 0 and beta 1. That's where the two unknowns are coming from, right? Two unknowns. So two unknowns. This is beta 0 and beta 1. Two unknowns. And then you also have two equations, right? And then this is where people get confused. Well, there's one formula here, right? How do I get two formulas? You get two formulas because you're taking partial derivative with respect to each parameter. Okay, so I'll repeat that again. You have two equations because you're taking partial derivative with respect to each parameter. If you have three parameters, then you have three equations. If you have four parameters, then you have four equations. Okay, so let's try it. Whatever this is, let's give that a cool name, right? Let's call that, well, here I used L, so I'll just say L, right? I'll use this letter called a calligraphic L. This means loss. So when I write loss, right? When I write loss, I'm talking about this entire thing, okay? Specifically this formula here, that's my loss. So two equations, two unknowns. What do I mean by that? Well, let's write it out. So first is two equation, two unknown. Well, the first thing is to take derivative with respect to, you can do whatever order you like, but you can say just beta 0 and then beta 1, right? So the first thing is to take derivative. So I'll say partial beta 0, and then your loss function, right? And this is partial beta 1, your loss function, right? So that's what you are, like two equations. And then you're like, okay, what does this mean? Well, you plug in a formula, right? So this is partial beta 0, and then you plug in formula. What's the formula? Formula is this thing, right? So I'm gonna be lazy just for a little bit, right? I'm gonna take this, I'm gonna copy, and I'm gonna put it here. There we go. Okay, and then I'm exactly repeating the exact same thing, right? This is a partial beta 1, paste, boom. All right. So then you're like, hold on one second. Equation means something equals something, right? What does this thing equal, right? You need to tell me what does this thing equal. Well, here's a question. Here's when calculus comes in, right? Let's say you have your loss function. It's some sort of plane, right? Let me draw it here. So that's 1, that's 2, something like this. So this is your beta 0, this is your beta 1, right? And then this is your loss, right? So it's gonna be some sort of plane, right? I'm horrible at drawing, but I'm gonna try my best. So it's gonna be something like this. It's kind of like a 3D. Oh, that's terrible. Okay. Something like this. You guys get the idea. It's kind of like a 3-dimensional plane. and then you can go like this, something like this. There's of course has to be some sort of spot in the middle. That's the lowest point, right? So this has sort of something here. Oops, something here. You can say this is gonna be global optimum, right? So what this means is lowest spot of the entire plane, right? It's the lowest spot of the entire plane, right? So if I draw a graph here, I'm not sure if I can draw it, like something like this. This purple plane is gonna be the lowest value of the entire function. Basically, this entire function, it all has to be above this purple point. Let's say this purple point is wherever. Let's say purple point is here, this value. Doesn't matter what that is. Let's say 0.001. Okay. Everybody else has to be above that. It has to be. That's what the global optimum means. It's the best spot. It's the lowest spot of the entire function. Okay. And then you say, well, how do I find that? Well, you take a look at with respect from beta 0, and then you take a look at this graph with respect from beta 1, and then you take derivative, and then you set to 0. Okay, so I'll repeat that again. First thing you do is you say, okay, let me move this to the left. Sorry, I'm moving things a lot here, but bear with me. Alrighty, okay, so all right, so first thing you do is with respect to beta 0 and with respect to beta 1, right? And then this is with respect to beta 1, okay? So if you're looking at this graph with respect to beta 0, it's kind of like you have an eye, right? Let me use a different color. Like you have an eye like this, and you're observing from this angle, right? So when you do this, you're not gonna see beta 1, like you don't see it. You only see 2 dimensions, right? So what's gonna happen is you're gonna have beta 0, and you're gonna have your loss, and that's it. And your function is gonna look something like this. Oops. Your function is gonna look something like this, right? And then that's your loss, right? That's your loss. And this is your beta 0, right? Because you're observing from the beta 0 axis. You're not gonna see beta 1, right? Because beta 1 is hidden from the angle, right? So then you take derivative. If you're here, the derivative is like this. If you're here, it's of course steeper. Derivative is like this. If you're here, maybe derivative is like this. Until you're here, the derivative is like this. What is this? Slope is 0. That's how I know it's the best spot. The slope is 0. 0 means what? 0 means flat, right? The slope is flat. That's the best spot. So if you're looking from beta 0, the best spot is what? The best spot is you take derivative with respect to beta 0, and the function is 0. Okay? So this means what? This means this is 0. So you set this as 0. Okay? Now we're gonna do the exact same thing with beta 1. So I'm gonna switch a different color. Let's see. I'll do green color. All right. So let's observe from this angle, right? You have an eye here, that's your eyes, and you observe from this angle. When you observe from this angle, beta 0 disappears, right? You're not gonna see beta 0 because you observe from this angle, right? So what that means is maybe you're gonna have some other function, right? So that's beta 1, that's your loss function. Beta 1, let's write that down. Loss function, let's write that down. This is like taller, right? This is like shorter, right? So it's gonna look something like this. Does that kind of make sense? I'm kind of messing things up here, so let me get rid of that. And so let's say let's come up with oops, something like this, right? So this part is left, this is right, because you're observing from this angle, right? Like this angle. So if you're observing from this angle, the left-hand side, maybe it's higher in numbers. The right-hand side, maybe it's lower in numbers, right? Higher, lower, right? What's the best spot? What's the optimal spot? the optimal spot is where you take derivative, it's 0. Okay, so derivative, if you're here, you take derivative, it's not 0, right? Because it's negative. If you're here, you take derivative, it's still negative, right? You're here, you take derivative, it's positive, right? None of them derivative are zeros. You're only here, and when you take derivative, the slope is 0. That's how you know it's the best spot. So that's why you come here, you say, I'm setting this as 0. All right. So then you have what? You have 2 equations, you have 2 unknowns. Done. That's it. Then you go ahead and solve it, right? So this is the setup, right? This is the setup. Basically, what we're trying to say is a very simple story. What we're trying to say is you have a loss function. Loss function could be higher dimensions, 3, 4, 5, 6, you name it, right? But in terms of just teaching and demonstrating the idea, I can't draw like a 4-dimensional space on a 2-dimensional paper. But the best I can do is draw a 3-dimensional graph, right? So I draw a 3-dimensional graph. That means what? That means you have 2 parameters, beta 0 and beta 1. Beta 0 is one axis, beta 1 is another axis. Once you have these 2 axes, you say, well, I'm taking the partial derivative. What that means is you're observing the graph from one angle, okay? And when you're observing the graph from one angle, the function, of course, changes a little bit, right? They're not going to look exactly the same. And then whenever you observe from beta 0 or beta 1, you say, okay, what's the best spot here? And turn out the best spot is the spot where the slope is 0. Okay, so that's the story here. So once you set up these 2 equations, you set up 0, done. You solve it. And that's it. So if you're looking for the slides and you want to look for the solution, here's a final solution for you guys. So after you go through all that math, right? So this final solution is going to be something weird. The final solution is the sets, right? Beta 0. Typically, people write beta 1 first. So this is going to be beta 1, beta 0. Actually, let me write it. And it's going to be something weird. So this is going to be summation I from 1 to n. And then this is xi minus x bar, yi minus y bar. Okay, and then over, and then the variance of x. So summation I from 1 to n I minus x bar. Okay, so if you solve it, the solution of beta 0 looks exactly like this. And then the solution for beta 1 looks exactly like this. The solution for beta 0 is y bar minus beta 1 hat x bar. And then beta 1 hat, well, technically this is beta 1 hat, this is beta 1 hat. And beta 1 hat, you kind of know, right? It's exactly this thing. So you just take this and plug in here, right? And then if you want to, you can simplify it, but you don't really have to because people will understand what this means. So that's kind of like how things work when you're going for the first solution, right? The first solution is what? First solution is this one, right? 2 equation, 2 unknown. Okay. Then we also have gradient descent. Gradient descent is a different way of searching for the best solution, and I'll briefly walk through that as well. So when it comes to gradient descent, there are 2 ways to understand this. The first one is to essentially write out the algorithm. The second one is to draw a graph, and I'll do both. Okay. So now that's the first one, right? Check. Now we're going to do the second one. The second one is gradient descent. I'm going to write it here. All right, second one is gradient descent. So when it comes to gradient descent, first of all, you write out the algorithm. So you need to at least know on the first name basis what the algorithm is, and then you draw the graph. Okay. First things first is, of course, to understand what is the loss function. So you're always going to have to define loss function. In this case, we talk about loss function. It's mean square error. So you choose mean square error. So then that's going to give you something like this. I from 1 to n, yi hat squared. And then the second thing is you take a look at your gradient. So compute gradient. And the gradient, we use this this symbol here called this is called nabla. Let me write it better. So this triangle is upside down. This is a Greek letter called nabla. I'm running out of space here, so I'll write it here. Okay, and then this one is called sigma. There are a bunch of other things. Of course, everybody saw this before, right? This is called delta. And then whatever, right? They're more than that. But here, the upside down triangle is called nabla. It's this guy here, nabla. Nabla means exactly what we've done above, right? Partial derivative or gradient of your loss function. The general way to say it is the gradient of the loss function. But most models have more than one parameter, right? Deep learning has hundreds of thousands of parameters, right? So that's why people also say partial derivative with respect to whatever. So you can kind of just write it out. So the gradient of your loss function is going to be essentially partial derivative with respect to your parameter vector. I'm messing this up. This is supposed to be a W vec, and then your loss function. And I'll explain what this means. So it's yi minus yi hat squared. And then you need to say where W vector is a set of W0 and W1. Now I'm changing notation a little bit, right? I'm not writing beta 0 and beta 1. I'm writing W. But if your model is a linear regression model, the beta 0 is just your W0, beta 1 is your W1. So here, you can think of this as beta 0, you can think of this as beta 1. The reason I use the letter W, I changed letter, right? Letter W, W0, W1, right? It's because in the neural network, the W is called parameters, and W is the letter that's go-to letter for parameters. The B actually means bias, so that's why people write B and W separately, so you know that okay, this is bias, this is the parameter, so you don't get confused. In linear regression model, the beta 0 by itself sometimes is called a bias because that's the intercept of the model, right? So so let me just put a small remark here. In linear regression model, beta 0 is intercept. It can also be called bias. However, in neural network model, W is parameters, whereas your B, or sometimes people write beta, this is your bias. So people want to avoid this confusion here, right? That's why you use different letters. Okay. So just bear with me and accept, just temporarily say that we use W, okay? Even though in linear regression, that's what we're doing right now, doesn't really have any difference. But let's just say temporarily we're using W. And when that happens, now you're at your last step, right? It's an algorithm. So algorithm means what? Algorithm means you have to converge, right? That's the whole point of this. In the step that we have above here, you don't really have a sense of convergence because there's no algorithm, there's no loop, there isn't anything like that. And the reason is in this particular setup, we have a two equation, two unknown. And what that means is you can always solve for a final solution. The reason is simple. You gave me two equations, two unknown. I can always solve it, right? But the reason is simple. But the problem is, in higher dimension, you don't always have a unique solution, and you don't always have a fixed way of solving. So you use gradient descent. So what is gradient descent? Gradient descent is saying, okay, at each step t, let's use s, because s means step, right? At each step s, w vector s is updated by w s minus 1 vector minus this letter called eta and gradient of your loss function. Right, there are like some a bunch of notation here, but let's break this down. Okay, so eta, first thing is eta. Well, let's talk about W first. W vector means W0 and W1. Vector means a set of vectors, right? So this symbol up here, this means vector. Okay, so vector means a set of different numbers. So let's write that out. This symbol up here, this means vector. And what that means, it's a set. That's what it means. And then the next thing to explain is the step size, right? There's the S has a step size, right? These W's, they have a step, right? Step S minus 1, right? So this S means step in the algorithm. If your algorithm has 1,000 steps, then S is 1, 2, 3, 4, all the way to 1,000. If you're 2,000 steps, then it's 1, 2, 3, 4, all the way to 2,000. Okay, and we're gonna use this S as some sort of stopping rule, and I'm gonna show you guys how that works in just a sec. But before we go there, we have a couple more things. This we haven't talked about, right? This is called eta. ETA, eta. This is a Greek letter, and again, this is a Greek letter. Okay, eta. Eta is usually a small number, and the reason we have this eta thing here is because sometimes the gradient is either too small or too large. It's not really at a good spot for us to update the parameters. So we have this eta term here to change the gradient numerical value, smaller or larger, doesn't matter, right? Smaller or larger, and then this way it will allow us to do the gradient descent faster. Okay, I'll explain in just a second using graphs. But typically you can kind of assume that eta is a small number, so 0.0001, something like that, it's a small number. This is of course an assumption, right? If you don't like this number, you change it to 0.0002, 0.0003. It doesn't really matter because it's just a small number. Okay, so then with that being said, now we can kind of expand this formula a little bit, right? Because we talked about two unknowns, right? Two unknowns. I have to do this for both formulas, right? So what that means is here, I'm abusing notation a little bit, right? But let me correct myself. This nabla, it's really with respect to what? To a W, right? It should really be like that. So the reason I say that is because you have two unknowns. So when you take derivative, you need to make sure that you're taking derivative with respect to that one. Okay. So if you want to expand this, it can be something like this. This is a vector. So this is a W0 and W1. But then it's a step size S, right? So you need to be a little bit careful. You say comma S, comma S. And this is going to be what you're updating. And same thing here, W0, comma, S minus 1. W1, comma, S minus 1. That's the vector. And then when you do your eta is a constant, so that doesn't change. So you can just write that in the beginning. And then this is, of course, a vector form. Vector form of the gradient of the loss function, and pay attention here, it's with respect to that particular parameter. It's beta 0, you take partial derivative with respect to beta 0. It's beta 1, then take with respect to beta 1. So this is going to be gradient, so partial beta 0 loss function. And this is partial beta W1. This is y hat. Right? So that's going to be how you update this algorithm. So once again, you're updating W0 and W1 together. Okay, so this way, essentially what it feels like is, and I'm gonna do my magic again and copy this graph. So bear with me, I'm gonna copy this. And then I am going to go down here and paste it here. All right, there we go. Okay, so now let me make it bigger. All right, so all these junk, I can get rid of that because we don't need to use this. I'll get rid of this, get rid of that, get rid of that. I just need this graph here. All right, so you're at this graph. Let's say you're at this spot, right? Let's say you're at this spot, this blue dots here. So what you're gonna do is you're gonna do gradient descent. So you're gonna look at the slope, and then in this case, it's kind of like a plane, like this, like a small plane. And then it tells you this is the direction, and then you update both beta 0 and beta 1 together. So what that means is this vector like this is a combination of vector here and vector go down, right? It's a two-dimensional, right? So it's kind of like if you have a graph like this, and I say, hey, that's a vector. What is that vector breaking down? Like, how can we break that down, right? You break it down to this, that's one vector. Break it down to here, that's another vector, right? So what's this vector? This vector can break it down to 1 and 2. So that's exactly what we're doing. So you tell me 1, you tell me 2, I can tell you exactly what that is, what that combined vector point in the middle is, right? And then you do the same. Now you're here. You compute the direction again, vector, go here. And now you're here. And then you compute the derivative, it goes here. And then eventually, it will come to here, which is the global optimum, okay? So this purple dot is the best one. Right? So that's what gradient descent means. Now, in addition, you also have this confusing point eta, right? Eta just means that how big these steps are. If these steps are too large, you have an eta, you tune things down a little, right? You just do this much, and that's it. If beta is too small and you're not learning anything, or you wait for forever, right? Then you use eta to make it bigger, right? So that's kind of the idea. Usually, based on experience, people tend to like to make it smaller, just to make sure that they cover like all different directions before they know where to go. Okay, so typically people will zigzag. You go here, you go here, you go here, you go here, you go here. It's almost unlikely that you magically know where to go in the beginning and then you just go a straight line. Usually it's zigzag. Yeah, so that's kind of how things work here. All right, so that being said, hold on a second. Before I do the break, I think there's a question. Somebody asked, what is the derivative? Oh, that's a good question. So in calculus, or it doesn't have to be calculus. So a derivative means this. So when I write this symbol here, so when I write this symbol here, let's say x, right? And you have a function of x. Let's say the function is so I define the function to be 2x cubed, right? So this is exactly just the derivative to take the prime of this. So this is going to be 6x squared. Does that make sense? So this action here is called the derivative. And the partial derivative means that sometimes you have more than one unknown. So you take the derivative with respect to that one only. Okay, so let's say I define another function. That's f of x and y. That's 2xy, let's say it's that, right? And then I will say partial y. So this means that I am taking a function, I am taking a derivative of f of x and also y, right? There's two inputs. But I'm only talking about y, only with respect to y. So all the other part, even though x is unknown, we treat it as a constant. So the derivative of this is 2x cubed y prime, but with respect to y, so this is going to be 2x cubed. And that's it. Make sense? Let me know if this is still confusing or if there's a still question here. All right. Awesome. So let's take another 10-minute break, and then when we come back, finally, we're going to be talking about Python. And I hope that all this stuff will give you guys the mathematical foundation to set you guys up of what is machine learning, what is making prediction, and how to train your model, and so on and so forth. If you still get confused, don't worry about it. We're going to come back and reinforce all of this for essentially the rest of the program. we're going to come back to this again and again and again. Because this stuff, it stays. The philosophy is exactly the same. The algorithm changes, the function changes, but the philosophy stays exactly the same. Alrighty, okay. So I'm looking at my clock at 6:57. Let's take a 10-minute break. So let's come back at 7:07. So I'll see you guys in 10 minutes. Hello? Hey, let's give a few minutes for students to come back. Yeah. Hey everyone, welcome back. All right, let's give just a few more seconds for people to join. All right, so let's get started with a little bit of Python code of linear regression model. All right, can you guys see my screen? Good. Awesome. Thank you. All right, so before we get started, let me just say a few words about linear regression model. So I think someone asked me a question about taking derivatives. So I just want to cover a little bit about that. Let me make sure this is the notes for today. It's July 19th. All right. So this is kind of like the graph that we kind of demonstrated in whiteboarding session or earlier in like the previous hour. So you have all these dots means each particular data point, right? And they have a certain distance towards the line. And obviously, your goal is to do whatever you can do so that the distance is small. And one thing you can do is to change the slope. So that's essentially kind of like the core idea of what the linear regression model is. So somebody was asking me a question about derivatives. So let's talk a little about that. So the question is derivative. Well, suppose your function is, can you guess this? There we go, okay. Suppose your function is, let's say f of x, right? It's x squared. Then the derivative is, well, let me just say the English sentence first, and then I'll write the math formula. So you say the derivative of this function is, and then you say 2x, this is based on the rule of the derivative. So rule is let's say parentheses x to the power of say n is nx n minus 1. I should really say derivative. So this is parentheses dot. So that means prime, right? You're taking derivative. Okay, so that's kind of like the basic rule. So of course, if you have, let's say you have multivariate, right? If you have two inputs for the function. So suppose, then let's say, suppose you have two inputs for the function. For example, a function is x comma y, two inputs, right? X comma y. Let's say it's defined as whatever, like x, y cubed, right? So x, y to the power of 3. Now x, I'm not writing it out, right? But really, this is to the power of 1, right? Power of 1. So usually people don't write that, so this is power of 3. So what this means is you have two inputs, x and y. Y has power of 3, right? So now the question is, when you say derivative of this function, that sentence is going to be very vague. I don't really know what you're talking about. You need to tell me with respect to x or with respect to y, because there are two inputs. You need to tell me which one it is. Okay, so the derivative of f, when we write the c dot, this just means a dot in the middle. It just means whatever argument that is. Okay, the derivative of this needs to be stated with respect to. If you don't tell me with respect to, I have no idea how to do the derivative. Okay, you have to tell me that. So the derivative of this function needs to be stated, stated with the words or the phrase with respect to. So that's a full sentence. All right. So for example, you can say derivative of f with respect to x. How about that? So then I can do xy cubed, right? Prime, right? Now with respect to x, right? X means with respect to x means x is the changing factor, right? Everything else is constant. Okay, so this is basically the same way as if you were treating this y cube as a constant. Doesn't matter what y is, that thing is a constant. So it's almost the same way as I say ax prime. What is that? Well, that's just going to give you a, right? Everyone follow this? Any questions? Question? Now's the time for question. Anybody still confused with this? All right. So and then of course you can for another example, right? Derivative of the function xy, and again you have to tell me with respect to what, right? With respect to y, then I can do the same thing, right? Xy cubed. Now I can take it prime, but now it's with respect to y, right? So that x doesn't matter what that is, it's a constant, right? So you are doing what? You're essentially following this rule, right? So it'd be as if you're doing ay cubed prime. That's kind of what you feel like you're doing. And then of course this is going to equal to 3ay to the power of 3 minus 1, right? Because this rule here is n minus 1, right? So 3 minus 1, that's going to be 2, right? Any questions so far? Question? All right, awesome. So yeah, so hopefully this is clear, and this is a mathematics speaking how the rules work, right? But if you're asking me, well, what's the intuition behind it? The intuition behind it is really just a calculate the slope. That's it. There isn't really like why do you want to calculate slope? Well, it depends on what you're doing, right? If you're doing gradient descent, of course you need a slope. So that's kind of there's no strict, the math is a tool, right? Somebody asked me why do we have to do derivative? It's because we're doing gradient descent. And why do we do gradient descent? Because we want to find the best optimal point. Taking all those things away, why do I want to do derivative? I don't know. I have no idea. Right? You need to have some sort of motivation, right? The motivation here is gradient descent, and that allows us to find the best spot in the function. Okay, so that's why we do this. Okay, so with that being said, now we can just run this. Let's go to this notebook so that everyone is on the same page with the coding that from yesterday is essentially loading data, right? Do some basic plots using the OS, which is Linux system command language, to navigate to different folders, right? So we talked all about that yesterday. Today the goal is simple. Today the goal is to essentially I want to run you guys through. First thing is a basic linear regression model, and then we're going to talk about a couple of ways to make this thing more complicated. Okay, so basic linear regression model, one feature, right? One variable, x, that's it. In this case, a is your slope, b is the bias, or b is the intercept. Okay, so what that look like is you're gonna create x, and let's break this down one by one. Okay, so first thing is what is RNG? RNG, right? You print out, it's gonna be some sort of random state function. It really just gonna give you a number that is essentially coming from kind of like a normal distribution. It's kind of like random numbers. So here, how we use this function is we call a .rand n function. So what you're gonna do is where's my dot? Oh, .rand n This by itself is obviously a function, right? It says it's a function. The function takes some sort of arguments, let's say 50. It will just give you 50 data points. Okay, 50 data points. And this, I believe, is, can I do, is that a thing, darkest? That's not a thing. How about this? Okay, I guess you can do that. So I'm trying to throw this in the function. So plt.hist. It's going to give you a function like this. So it's kind of like a kind of normally distributed, but not really. But you can kind of take a guess that the average is 0. Okay, so that's kind of what this is. It's kind of like just means noise. Okay, because if you don't add this, it will be what? It will be a straight line. Okay, so I can show you guys what that looks like. But first thing is that's gonna be where data is coming from. That's gonna be the x from 0 to whatever, like 10 or something. And then you also have your y, right? Y is gonna be a relationship. Let's temporarily say it's slope of 2 and intercept of -5. Okay, so A is gonna be 2, B is gonna be -5. So I can say thus your model is y equals to 2x minus 5. Oops, $sign. So that's what your model look like, right? And then obviously you're gonna have to add in some noise, because if you don't add this, it'll be a straight line, right? So I can temporarily get rid of this, and then I say y equals to only 2x minus 5. I don't add anything, right? Then it'll give me a straight line. Okay, so that's kind of the situation here. So in this case, you can kind of think about this function 2x as a real relationship. We're lucky because this is kind of like a fake data that we're creating, right? It kind of falls on a straight line. You add a little bit of noise. It will essentially give you somewhat variance, like a somewhat normal looking variance. Okay, so that's kind of the idea here. Oh, somebody asked me what the $sign means. $sign, when I'm typing this means it's a mathematical equation. If I get rid of these $sign, it won't look like a math equation. It will just look like letter y equal letter 2x minus 5. Adding this just means it's a mathematical equation. So it will kind of look nice like this. If you want to do $sign, that's also okay, but that will only be in text. If you want to do $sign, that means the function by itself, it's a line. Okay, I can write this up. So note, $sign, how do I do this? Like this. Means you are typing math equation. Single $sign means in text math equation, where double $signs means the equation itself is a new line. All right. Okay. So that's that, and that's what your data look like, right? Now your job. Now the goal is simple. The goal is to say build a linear regression. That's your x. That's your y. Train a model to learn about the slope 2 and whatever this -5 is, right? That's the goal. So we do have a real situation. We know what that looks like. Great. Oh, by the way, I forgot to explain this random state. This random state means set C. Okay, so what this means is it's essentially telling the computer that we are having a reproducibility of basically number 1, whatever that is. If you set 2, it's going to be a different set of random numbers. But as long as you set 2, you can always regenerate exactly those numbers. Okay, if I set 2, now of course it's still going to look kind of like that, but the dots are going to change, right? See, I run again, it's going to change. I run 3, it's going to change again, right? You just keep sampling a new data that's a random. But if you fix number 1, I can run this forever. The dot's not going to change, right? So that's kind of the relationship, why we do a random state. So that if you run it and I run it, we get the exact same number. Okay, so that's the difference. Cool, that's a good question. And then we can just get things started. That's a little draft that we did earlier. We can skip that. Okay, so the next thing I'm gonna teach you guys is called a function called a linear regression model. So all that crap that we do, right? two equation, two unknown, gradient descent, partial derivative, all that crap that we did. All of that is summarized in this one word, linear regression. It's a function existing on scikit-learn library. Okay, and this function essentially can tell you a whole lot of things, and we're going to show you how to use that. I think somebody else had a question. Are you working with data from a data set, or are you making it yourself? This data I'm making myself. So this X is created randomly. Right? It's a random data. It's not from real data. It's not from CSV. It's we created this on the spot. Okay. So that's a good question. It's a fake data, right? It's a toy data. Right? It's a toy data. All right. So this toy data is created to show you guys that the linear regression model can truly learn about this kind of relationship. So what relationship? 2x minus 5. That's a relationship. So in other words, we know the ground truth, right? We know in reality what the situation is, right? Slope is 2 and intercept is 5, minus 5, right? And the goal is simple. The goal is to build a model and learn that. So I said that this way on purpose because if I give a real data, we have no idea what this is. So if your model is good or bad, we can't verify it. Okay, you can only verify that with loss function, but that kind of defeats the purpose a little bit. So for this tutorial, I'm going to use this data just temporarily as a check. Okay, so obviously you're loading your function, and then the next thing is to call the linear regression model. Typically, this is the template for essentially the rest of the program. Okay, so you're gonna memorize anything. Memorize this. Okay, so what is this? The template, the typical template of machine learning is to set up the model and then do a model.fit. All right, that's the typical template. And if you're gonna memorize anything, just memorize this one line. If you forget about everything else, I'm happy. Right? Just please memorize this one thing. You have to define the model first, and then you fit the model. This has to happen. Right? If you forget this, then the entire class is kind of forgotten. Okay, so please remember that you have a model.fit. It always is like that. This is not going to change. So a model here, it's a linear regression model, and we specify that the intercept is true, so we allow intercept. If you say false, then it's gonna force this thing to be 0. So that's not gonna be accurate, right? Because we know that there's an intercept, right? So we allow it to be true, and then we define a model, and then the only thing you have to do is model.fit. And a model.fit, you just throw in the x, you throw in the y, and that's it. Super simple, okay? People might get confused. Well, what is this thing here, right? Let me show you what is this. So what is the input features? Well, y is a target, right? This is easy to understand. X, what is x? If I give you x directly, it's gonna be an array of whatever this is. Okay, so unfortunately, this is gonna be a little bit troublesome because it turned out that you're gonna have to turn this into kind of like a column. This is not a column. This is a vector. Okay. So what you do is, if you do this, you're gonna select pretty much all of the elements in the vector, but nothing happens, right? You need to tell the computer. You say, "Hey, I'm giving it a new axis." Then it will be a column. Okay. So if you can't really tell what the difference is, my recommendation is you do this. You do them side by side. So you do it without this, and then you say dot shape, and then you do it with this, and then you do dot shape. So now you see the difference. 1 is by 50, 1 is 50 by 1. So technically speaking, there's a column there, right? When I do comma, I just mean that you print out two things together. I think that was another question. Or alternatively speaking, you can say print this and print this. So then it will give you two lines. If I don't do anything, if there's no print here, let's say I just do this, then it won't tell me what the shape of the first line code is. Okay, so you better put it in a print statement, otherwise it won't show up like that. Sorry, I had a typo. Yeah, that's pretty well. All right, cool, awesome. Yeah, that's all the questions. Great. Yeah, so fit the model, and then next thing is you predict it, right? So you create your fake data and you predict it. So let's break this down. What is X? X fit. It's just a bunch of random numbers, right? And here we want to have very how do I say, very like very condensed, right? Because if you look at this 2.81, 2.82, or sorry, I missed it, 2.81, 2.82, 2.83, 2.84. So it's very condensed, right? Because in mathematics speaking, you can always fill in a number in between two numbers. That's what continuous means. But in computer science, everything is discrete. Because it's a computer doesn't know how to fit in infinite amount of numbers in between two numbers. That's not going to happen because computer has limited amount of memories. So this line space is just kind of reconstruct something that if you plot it out, the space kind of so small that we human eyes can't visually see it. That's all. That's all there is. So if you do this way, you're gonna get a bunch of numerical values that are so close to each other that almost look like continuous. That's really what it is. So you run that, and then obviously the next thing is you make a prediction, right? So model.predict. Okay, so the next thing you have to memorize is after model.fit, you can make predictions by using model.predict function. Okay, so if you're gonna forget anything else, please remember model.predict. Right, two things very important. One is model.fit. The second one is model.predict. That's it. Everything else, the entire machine learning data science community is based upon these three things. If you're gonna forget everything else, please memorize these three things. Let me move this side channel up. Oops. Okay, yeah, just message me if there's a question. All right. So yeah, so that's essentially the couple of things that's important. And then once you have data, you just predict it, right? You have a Y fit, and then you're like, okay, how accurate is Y fit? Well, you plot it out, right? That's the first thing you do. You plot it out. So when you plot out, you do two plots. The first plot is a scatter plot, right? That's the first plot. The second plot is just a very simple line plot, right? If you don't say anything, just say a plot, you will assume that's a line. Okay, then it's not gonna make any sense because think about it. If I do plot, it's gonna give me these like weird zigzags, like this. That's not gonna make any sense. Like I can't see what that is. So you have to change to scatter plot. And the reason is what? The reason is this is discrete. This is continuous. But this is computer science continuous. Basically, it's a condensed, very condensed numbers such that the space are so small that we can't see the space in between the lines. Okay, so it's not a mathematical continuous, Okay, so every computer science program, if you guys are going to major in computer science, there's this thing called Discrete Math in computer science. Every computer science major must take that class. It's a required class. And essentially they're gonna go into detail of exactly what this is. Okay, I'm giving you guys like the brief version. So once again, mathematical continuous, there's no holes in the middle, right? It's a straight line, and I meant it like a natural line. You can zoom in however you want, it's still gonna be a straight line. Okay, this way, if you zoom in, there are holes in the middle. How do I know that? Well, you take a look at the data, right? Where's my X fit? X fit is here, right? So you can take a look at the data, X fit. There are holes, right? Even though the holes is small, 7.21, 7.227, like what if I give you like a 7.216? That's kind of like in between, right? So there are holes in between. So that hole is too small that on the computer, on the plot, that is essentially this small of a plot, you can't really see it. So that's a difference, okay? All right. Pretty sure that's going to be an exam problem. Not in my class, but like when you get to undergraduate class, I'm pretty sure that's an exam problem. So forget everything. Please memorize this. Okay. So once you have a model, obviously you want to know the results, right? The result is the predicted slope and the predicted intercept. Okay, so you write it out, that's going to be this. So 2, we know the real model is 2, right? Where's my real model? 2. And the real intercept is -5. So you better get as accurate as you can to 2 and -5. And that's exactly what it is. So you have a 2 that's here and a -5. Well, it's close enough, right? This is -4.998, so that's close enough. Okay, so that's kind of the story here, right? The story is, you have a bunch of scatter plot, you build a model, fit the model, make a prediction, and then you plot it. It looks perfect, right? So that's what a dream case scenario would look like. Now, of course, in reality, there's going to be a bunch of other scenarios, right? So this is one form of transformation that I want to introduce to you guys, just to expand your horizon a little bit. The x that we talked about in previous model doesn't have to be just x. As a matter of fact, you can do whatever you want. Okay, you can do whatever you want. You can do x square root, x cube, x squared, x to the power 5. You do whatever you want. Right? So what all of that refer to is this function called the polynomial regression. So the polynomial regression is referring to the type of regression problem where you're taking an arbitrary x and then you're increasing the power term on this x. So power 1, power 2, power 3, power 4, you name it, right? You do whatever you want. So that's kind of what a polynomial regression is talking about. And the implementation of this is actually very straightforward. You can take your function, like import it directly from scikit-learn, and you can just run that. Then boom, you have your function here. And then let's create a small example. Let's say you have a small array of 2, 3, 4, right? Very simple 3 numbers, right? 2, 3, 4. You can use polynomial feature as a function. But first of all, you need to build up the polynomial function, and then you need to fit the transform, right? So once again, we're talking about similar setup. So if you're gonna forget anything, please remember this. It's the same setup as what we had before. We have a I don't want to say model because how do I say this? We have a I'll just say model. We have a model defined. Here we call it poly. Then we fit the data to this function poly to obtain the transformed data. This is where we use poly.fit transform. So it's the same relationship, right? Above what we have model and model.fit, right? It's the same template, okay? Here you have poly.fit transform, right? It's the same template. So what that means is you have your function first, right? Polynomial features, whatever. This 3 here means that you're using a polynomial of 3. So it's gonna go to power of 3, and that's it. If you do 4, that's power 4. If you do 5, that's power 5, and so on and so forth. This is going to give you very simple. It's going to give you power 3, right? So power 1, power 2, power 3. So what that means is 2 is going to give you 4 and 8, right? That's power 2 and power 3 on top of 2. 3, you have 9, that's power 2, and 27, that's power 3, and then so on and so forth, right? So that's how this function works. So now that you know how this function works, then what you're going to do is you need to build something such that you can use the regression and use the polynomial, right? You need to build something that you can use all these building blocks. So how do we put them together, right? So you call this function called the pipeline. Make pipeline. Okay, so you run that, it will give you this function called make pipeline. And the make pipeline is the first thing. It's the same thing, right? First thing is what? You do your model and do some sort of .fit, right? So once again, this is you build your model. Remember the template. You build the model first. here you build poly model. Then you do some sort of poly model dot fit, right? That's a template. You make your model, right? In this case, model is a pipeline, and this pipeline function is here. You throw in two things. One is polynomial features, which is another function up here that we just introduced, and the second one is a linear regression model. Okay, so it's a function that takes two functions as input arguments. And then you can kind of run this function. You will define this, and you can kind of print it out and just do a quick sanity check, right? What does the pipeline look like? Well, the pipeline looks like this, right? It's an array of functions that tells the computer what functions to use. Okay, and then you can here I have a couple of codes just to demonstrate the shape of X again, but we showed you guys up here, right? So it's the same thing. This shape of X, right? It's the same thing. So I'll skip that. And then here, let's create a different model, right? The new model that we're going to create here is some sort of sine function. A sine function is kind of like, how do I explain it? Sine function is defined kind of like in a cyclical term, right? Go up, go down, go up, go down. So it has certain cyclical flavor, right? What that means is it's no longer a linear regression model. It's now some sort of higher dimension structure, right? If you fit the line, you're not going to get any better, right? Because how do I know how to fit the line? Like, do I go this way? Do I go this way? Do I go this way? I don't know, right? So that's where polynomial regression is coming in. Okay. So in other words, you can also say this. When the data is nonlinear, you should what? You should first think about polynomial regression. That's kind of like the intuition here, right? So instead of defining your model as linear regression model.fit, now you're doing, okay, let me define a pipeline. Let me use polynomial features. And the polynomial features, I'm going to apply that on linear regression model. And then do mod.fit. Okay, so that's kind of what's going on here. If you run that, you're going to get this graph. The dots are the data, and the blue line is so the scatter plot, that's the data, and this plot, that's a line, that is the fitted value. So it's essentially the prediction. So this is data, this is the prediction. All right, before I continue, let me take a pause. Any questions so far? Let me check the chat. Any question? Good. All right. Cool. So so now with that being said, you guys already have the basic building block, right? You know linear regression. You know how to create the data. You know how to make a plot, right? And then from yesterday, we learned how to load up data, right? So I thought maybe to use the remaining section to talk about that. This part I'll let's see. You know what? Let's talk about this because I worry we might run out of time, but let's talk about this. So now you have your prediction. The idea is, well, how do you know how accurate your prediction is? There are a couple of things, right? First of all, there's loss function, but we don't want to just use loss function, right? Because that's what we use to find the parameters. In this case, it's a regression problem. A regression problem has its own set of performance metrics. Okay, so this is a concept here called the goodness of fit, or how excellent your fit is, right? So written here. This is essentially referring to some sort of model evaluation. Okay, so to do that, we need to define two things. This one, the first one is ground truth. That's just an identity definition of what y is. So just define that as your y, boom, and that's it. And then in addition, you also have predictions, right? Predictions is, of course, some sort of model.predict, right? So these things is exactly the same as what we talked about above. Once you do your model.fit, you can do your model.predict, right? So model.fit, model.predict. Okay, so once you have a prediction, you have your ground truth and a prediction, you can then make a comparison. So the first comparison is called R score, or sometimes you call it R square or R2 score. But let me define that first. So define that, and then you run this function, you will bring this function down. this function, the formula is defined here, but of course, we don't have to go into too deep into the formula. What the formula is saying is this. This is your overall variance in the bottom of the fraction. This thing on top, this is the essentially the variance of kind of like how different your prediction is from the ground truth. So this over this, that's essentially the portion of the variance of the error. And you use 1 minus that, that is going to be the portion of the variance of the model over the variance of the entire data set. So in the sense that this is going to give you essentially the goodness of fit, that's R squared, that's going to tell you how good this model is. If this thing goes to like 1, right, 100%, right? Think about what will happen. If this number is 1, then this fraction is super small, right? Let me write it out. Let's say this is 1. For this to be equal to 1, this needs to be equal to 0, right? 0 means what? 0 means this thing is small, right? So small means what? Small means this number is small, right? If this number is small, think about what can happen. Yi minus yi hat. This is a truth, right? Truth. This is a prediction. If this number is small, that means these two things are close to each other, right? That means you're a good model. Okay, so if you can make this happen, then you're smiley face. This is a good model. Okay, so that's what's happening here that we want to achieve. So when that happens, of course, that's a good model. Okay, so you run that. Basically, it's you throw ground truth in there, you throw prediction in there, then you're kind of done. It gives you the R squared, and you take a look, it's like 97%. So it's kind of like not that bad, right? It's a pretty good model, and you can kind of confirm with the graph. Of course, it's a good model, right? Because it's kind of like a simple data, and we kind of created knowing that this model can do well, right? So that's kind of just give you a sense of what a good model look like. What do I mean by good? 97%, that's good. Okay. Another thing, another function that you can use as a metric is called the mean absolute error. Okay, so we talk about mean square error, right? We talk about mean square error. But what is mean absolute error? Mean absolute error is referring to the difference that instead of taking a square, you're taking the absolute difference. Okay, so think about this. Why is there a difference? Why can't we just use 1, right? Here's the difference. When you do things like this, you don't really have a square, right? That's the difference. This is technically speaking to the power of 1. This is to the power of 2. Okay, so think about this way. When you're trying to predict like something like a housing price, right? Price is what? In a unit of dollars, right? $100,000, $200,000, that's a dollar, right? A dollar to the power of 1, that's fine. You can explain that. You tell me, right? You tell me, you say, hey, the mean absolute error, right? The error is $1,000. Okay, we can have a conversation. But if you say the error is $1,000 squared, like I'm gonna have to make a jump, right? I don't know what that means. I need to take the square root to recover dollar, and then I can kind of translate. Okay, 100. You say $100 square. I don't know what that means. I have to take square root. Okay, that drops back to 10. As I say, it's 100, and then you take a square root that gives you 10. Okay, now we have a conversation, right? You say, hey, the error is 10. Okay, now I can understand. Okay, so that's the difference, right? That's why there's a difference between these two equations. Typically, people do whatever they want. If you worry about the final interpretation of the unit of whatever this y target is, then you can use mean absolute error. But typically, people tend to use mean square error, no problem. It's just when it comes to the final unit that matters, of course, you need to use mean absolute error. Okay, in this case, I'm going to show you guys both. So let's run that. And then let's run the computation. It's going to give you 0.008. Same thing with mean square error. You run a function, it's going to give you 0.009, something like that. So that's kind of what's going on here, right? And the next thing that can be important is called percentage error. Okay, this thing is extremely important when it comes to stock market prediction or stock price prediction. So why is this interesting, right? If you're trying to predict stock price, let's say I'll give you an example. Let's say, where's my pen? Okay, so let's say stock price looks like this, right? This is the time, and this is your stock price. This is a dollar sign, right? Go up, go down, go up, go down, go up, go down, something like this. All right. And let's say your prediction is like this. Let's say you start from here, and your prediction is like this. So is it good? Is it bad? I don't know, right? You need to tell me. And then maybe your computer, right? Maybe you use mean absolute error, and then you're like, oh yeah, $6. I have no idea what that means, right? You need to tell me more information. Is it $6 on $100 stock, or is it $6 on $1,000 stock, right? Because they mean completely different things, right? 6 over 1,000, maybe that's a good model, okay? 6 over 100, that's not a good model, okay? That's too far apart. You're 6% apart, right? 6% apart is a very wide variance when it comes to stock price prediction, okay? So in that situation, you better use this type of performance metric. Otherwise, I don't really understand what you're talking about. Okay, is it a good model? Is it a bad model? I have no idea. Right? You tell me. Okay. So that's the difference here of all these different scenarios, right? And once again, why do we come up with all these things, right? People come up with all these things because each of these performance evaluation metric are designed to take care of different situation. Okay. So how do you know when to use it? Well, you look at your data and you let your data tell you, right? If your data is some sort of dollar sign and it's not stock price, it's a housing price, fine. Then you can use mean absolute error. If your data is stock price, you better tell me what the mean absolute percentage error is, right? Because stock price can be $100, can be $1,000, and the $6 error can be a different percentage depending on what your stock price is. Okay, so all that matters and just depends on what data you're using. But here I'm giving you all the code. Okay, so you can work that out as well, and then you can check out the mean absolute percentage, and then maybe you have some sort of estimate, right? In this case, is what, like 24% on average. So is that close? Is that far? Well, it depends, right? It kind of depends on what you're looking at. So you can kind of look at the model and you're like, well, sometimes prediction is here, sometimes prediction is here. But you're talking about 0.5, right? So if you miss it, 0.25, that's automatically like a 50% difference, right? So in this data, if you get 20% or 24%, I'll probably say it's not that bad, okay? So that's kind of the idea here. So, the reason I'm showing you guys all of this is because, well, A, the different scenario. It's up to your own choice which loss function to use based on different scenarios. And B, there's no strict good and bad. It's not like, oh, yeah, 20% is a cutoff. It's better, if higher than that, it's good. Otherwise, it's bad. No, there's no such thing. It all depends on how you carry out your analysis. And typically, people do two things, right? A benchmark and whatever new model that they want to propose. Okay. The last thing I want to show you is kind of like a playground. So we know that you can load in the sample data, right? In this case, it's a California housing data. So you can quickly run through this. You can load in the training data. You can load in test data. Check out dimension. It's a 17,000 by 9. The test data is 3,000 by 9. And then, of course, this has to be 9, right? You can't train a model that has 9 features, and then you go to test that it has like 10 features. That's not going to work, right? It has to be 9 features. You can print out the header. Of course, this is the top 3 rows for both training data and test data. This, I trust all you guys can figure out. I won't bore you with this. Obviously, the first thing you can do is a univariate model. The univariate linear regression model, it's you pick a variable, right? Exactly which one to pick, I have no idea. You tell me, right? You tell me. You can pick any one of these, okay? Is it going to make sense? Is it going to be a good prediction performance? I have no idea. No one knows. No one knows before you try it, okay? So I'm going to repeat this a lot, and you might get sick of hearing this, but of course I'm going to have to say it again, because this is the truth, right? Most of the questions that students answer it's kind of like trial and error. I know that it's kind of like no one likes to hear the answer, right? Trial and error. Why can't you just tell me a correct one and then I'll just do that, right? No, like that doesn't exist. I wish it does, but it doesn't. There's no such thing as a correct answer or correct model for that sake, right? And there's no such thing as a correct features. Why don't you just tell me, let's use the median income, I build my model, done, right? No one knows what that is, okay? So here's basically a take home for you guys, right? Median income is kind of like an arbitrary guess, right? I look at this, I look at the data, and I'm like, oh yeah, median income is one of these guys, and then it's here. Great, let's use it to make a prediction. Okay, it's my own choice. It's not the right answer, it's my choice. Okay, my choice does not equal to the right answer. Okay, and I'm gonna say this again, right? Everything that all your professors said, right? Everything professor said, it's what the professor said. Okay, it doesn't mean the real answer, doesn't mean the correct answer. Okay, same thing goes to your parents, professor, whatever thing that you heard from whatever book, right? It's whatever, it's the John Doe said. Okay, it's not the truth. Okay, please drill this in your head. This is the important part. Whatever textbook said, that's just from that source. It doesn't mean the ground truth. The Mother Nature do whatever it does. Okay, you don't know that. No one knows. Okay, so this is again, median income is my choice. Okay, your job is simple. Your job is to question my choice. You don't have to do median income. You can do whatever you want. You can pick any of these columns that you want to build your own model, and you can see how accurate that is. Okay, if you don't like median income, change it, right? Take this population, copy, right, and come here, change it, right? Then you have a different model. Okay, it's just that when you change, obviously change at both places, right? Because you can't change training set and then you do something else, test it. That's not going to work, right? The feature has to match. So yeah, so let's try it, right? Let's go back to median income, run that. So now you have your training data and your test data, everything's clear, right? Everything's clean. The reason we separate training data and test data is because we want to build our model on one set of data called training data. And as of this point, all of the observations in the test set, the model hasn't seen yet, right? So whenever you do all these fancy evaluation metrics that we introduced here, right? Please do it on the test set, because test set are the observations that the model hasn't seen before. It's an honest evaluation. There's no cheating going on, right? It's not a pure memorization, right? It's like you're going to the exam, and I'm not gonna write an exam question that's like exact same as your practice exam. Right? What's the point of that? Then you can just memorize the answer and you get the points, right? That's not how things work. That's not how you learn, right? Chances are I'm going to give you a different sets of questions, such that the questions are slightly different, but hopefully it's using the same theory, right? So that's how you learn in the exam, right? And that's exactly what's happening here. So you have a training and testing. Basically, one is your practice exam. This is your practice exam, and this is your real exam, right? Training and test. And whenever you do your model evaluation, do it on test set, okay? So you set all that up, right? Now you're good to go. One thing I want to tell you guys is this thing called normalization. Normalization is one of the important assumptions in a linear regression model. And the idea comes from this. If I give you a data set, let's draw this, right? If I give you a bunch of scatter plot, and then you draw a line, right? What's the difference? We talk about difference, right? These purple lines, that's the difference. That's the error, right? So one important assumption is if you put these errors together, let's say we put it in a straight line, right? If you put these errors together, some are positive, some are minus, right? That doesn't matter, right? If you put it together and you observe from here, right? You observe from horizontally, this is gonna fall under a normal distribution. Okay, so what this means is linear regression model does the best when the data is normal. If the data is not normal, you can still run the linear regression model, but because this assumption is violated, then you can kind of expect that the performance won't do as well as it should have done. Okay, so that's why we kind of tampering the data a little bit and do a little data engineer to make sure that each of these columns are normally distributed. Okay, and when I say normally distributed, I'm talking about subtracting mean. So your x subtract the mean and divided by standard deviation. Okay, so that's what's happening here. So that's your average and that's your standard deviation. And do the same thing for training tests and test set, and you can do the same thing for y as well. This probably doesn't matter that much, but I'm gonna do it anyway, just to show you guys what the difference is. And then the next thing you can do is you can run through the SciPy library. It's gonna be kind of like a similar library as what we had above. It's gonna be slightly different because this library actually only allows you to do univariate model. So I won't be able to show you the rest of the code because it's about time. But you could run through these functions. It can essentially give you intercept, the slope, right? Which are here. And then you can also run through a couple of different things we're going to talk about next time is the correlation, the p-value, and what standard error means. So that's about time of the class for today. I think we are pretty much on track, so I'm pretty happy with today's progress. Any questions? Cool. All right. So again, there's no homework. But if you ask me what is some of the things that you can do, you can try by yourself. I will say this. If you want to be familiar with the material, I will run through this entire script again. And at each spot, I will try to play around with the model and change it myself. Toy data, I won't say much because that's toy data, right? You do whatever you want. For this data, this is actually a real data. So real data means, this California housing data, it's a real data. Real data means you don't know what the ground truth is, right? You don't really have, like here, we know what the ground truth is. Let me go back up. Like I know the relationship, right? So if it's right, if it's wrong, I know. I know that, right? I can look at this results. I know it's right or wrong, right? This is not the fun part, right? Because you know what's right or wrong. So the fun part comes when you're loading data and you have no idea what's right and wrong. And all you have is the model and the way that you take care of the data, right? So a couple of things that you can try. Variables, filter change whatever you want. Normalization, you can run it, you can not run it, do whatever you want. So you can either run it or you can skip it, right? And then when you go through this code, I will probably just refer to, let's see, I will probably refer to this error down here. This is called a mean absolute error. Maybe I should write this down. This is mean absolute, MAE. So right now I'm seeing what 0.55, right? So tomorrow, when we come back, we're gonna do a quick poll, and we're gonna see exactly what you have done up here. You do whatever you want, right? Do whatever you want, and we're gonna send out a poll tomorrow in class to check the performance of this one, and we're gonna see how different the number is for the entire class. Okay. So the to-do list is essentially run this code, do whatever you want, change features, especially this, right? Do whatever you want, right? And at the end of the day, you need to get to a mean absolute error, right? Mean absolute error, not MSE, not the other thing, right? Mean absolute error. And then we're gonna come back and do a poll of basically a distribution of this entire class, how different the answers is. So I'll set this as a to-do list, and then I'll send this out to you guys in Slack. Work out the notebook and compute this answer. The goal is to get this number as small as you can. The smaller, the better. Okay. All right. That's it for today. I'll say over for questions. But if there's no questions, then you guys are good to go. Oh, by the way, let me give you guys a survey. Sorry, I forgot. Please fill out a survey and let me know how I can improve the class. And if you have things you want to say about your recommendation letter, now is the time. What I typically do for the survey is, make sure that, obviously session 2, right? Everything else I don't much care. I care mostly about these 2 questions. The things you like, obviously I want to know that, right? The things that we can improve, right? The things you don't like, or maybe things that you get confused and you can't follow up, or anything like that, let us know, right? We want to improve ourselves as well. And we do read this. I read every survey myself. line by line. And then my idea is I kind of try to get what the student need, and I include that in the class. So hopefully this way it can be more absorbed well by the students. Yeah. All right. So yeah, really appreciate it if you guys can fill that out. And again, I'll stay for questions. If not, then once you're done, you can just feel free to drop out, and I'll see you guys tomorrow. Take care.
See you, Professor.
See you, Sam.